So the last section I'm going to talk about has one little twist with it, and it's dealing with something new called a slant asymptote, but the first part of everything is completely the same. So to start with a graph, we're going to talk about first the y-intercept. So if we're going to talk about the y-intercept, we're going to talk about where x is equal to 0. And if we let x equal 0 for this whole thing, we're left with -2 over -1, which is going to be a +2. So our x-intercept is 0, +2. Or our y-intercept, excuse me. Our x-intercept is where the y is equal to 0, or where the numerator is equal to 0. So where this is equal to 0. So I'm left with x minus 2 times x plus 1. So what I'm left with is the two options of -2 or +2 or -1. So my two x-intercepts are these two, 2, 0 and -1, 0. Now, if we talk about horizontal asymptotes, we're talking about where the degree in the numerator is larger than the degree in the denominator. So there is none. The vertical is where the denominator is equal to 0, and that is when x is equal to 1. So that is a vertical asymptote. So in terms of this graph, we have a vertical asymptote at 1. There's my vanishing lines here. We have a y-intercept at 0, 2. We have an x-intercept at -1, 0. And 2, 0. Now this last part, this is new, what's called a slant asymptote, and this is particularly new. And what this means is that if the degree in the numerator, so the degree in the numerator is exactly one more than the degree in the denominator. So if the degree in the numerator is exactly one more than the denominator, then this graph follows what's called a slant asymptote. And the way that you find this is by using synthetic division. Now you might say, what does that even mean? Well, I'm going to take the expression and divide it. So I'm going to take and divide that whole thing. I shouldn't say synthetic division. I'm just going to say division. But because it's a linear division or divisor, I'm going to use synthetic division. So what I'm going to do is I'm going to take 1, -1, -2, and I'm going to divide that by x minus 1. So I'm going to put a 1 there. So, if I divide this, what I get if I expand this so it's as expanded as possible, I get x minus 2 over x minus 1. Now you might say, well, how does that even help me with this problem? What is the point of doing that? Well, what this is telling me is that over the long run, since there isn't a horizontal asymptote, that the graph tends to follow this what's called slant asymptote. Okay? So how does that look? Well, this graph is going up like this, so it's going to go down and follow this imaginary line that divided evenly into it. Okay, this x-intercept is going to go up, and it's going to follow this imaginary line here. It's going to follow that line, and then it's going to go back down towards this vertical asymptote. A slant asymptote is kind of like a horizontal one. It creates a guideline as x gets larger and smaller. And this only happens if the degree in the numerator is 1 more than the degree in the denominator. And the way you find it is by using division. Okay, and we talked about that from the last chapter. So the connections that we talk about tend to show up. So when we talk about something like this, you know, when I get to the checkpoint, you'll have to see that, well, this is a degree 2, well, this is a degree 1, so that means there's no horizontal one, but there's going to be an asymptote that the graph tends to follow as x gets larger and smaller. So let's talk about this last problem. It says, a rectangular page is designed to contain 48 square inches of print. The margins at the top and the bottom are at 1 inch deep. The margins on the side are at 1.5 inches wide. What should the dimensions be so that the least amount of paper is used? So what I'm going to do instead, because the way the book models this is you have to value this from a graphing calculator standpoint. So what I'm going to do is I'm going to show you an equation that models this and then show you how your calculator can do this if you want to see in class. Because not everybody has the graphing utility or calculator to do this. Now, if we're looking at a piece of paper, we know that the top and the bottom are brought down 1 inch. So they're brought down 1 inch. And the sides are brought in 1.5. So what we really have is this dimension here that's x and this dimension that's y. Now, in terms of the area, we know that the area is going to be a value of print. So if we take x times y, we're going to get 48. But now we're changing the result of this. Okay? We're taking this value and we're subtracting the margins. So we're actually taking x and subtracting 2 from it. And then we're taking and we're subtracting 3 from y to get our area. Okay? So what we need to figure out is we need to figure out just exactly how to represent this in terms of one function. So what I'm going to do is I'm going to rewrite this in terms of one variable, just like our problem on our quiz where we write this in terms of one variable. So I'm going to plug this in for y. So what I have is x minus 2 times 48 over x minus 3 equals my area. So if I multiply this all through, what we're going to get is an equation or a function that models the area for this. Now I'm taking into account that I am subtracting the margins. what the book does is they take into account and add the margins to create more of an area. So what you could do, and this is totally different, if you want to add the margins in, you can say, well, shouldn't I just be adding these instead because we want to use more of the area of the paper? Well, it's one way or another. This is kind of one of those tricky problems that it's kind of hard to decide if it used to be subtracting the margins or adding them, and things like that are just kind of hard to just kind of look at and say, yes, we got to do this, or no, we have to do this. But I would look at this from the sense of, if we're using these margins, then you've got to take them out. But the book is looking at them and saying, well, if we're going to take these margins and include them, then I got to add it. So either way, you're going to create a function with narrowing the margins and excluding them or including them. So this is changing it so that we're including the margins versus not. So if I multiply this all through, what I'm going to get is x plus 2 times 48 plus 3x over x, or x plus 2 times 48 plus 3x all over x for my area. Now, when you get to this point, it'd be hard to try and say, well, what is my minimum amount of area for this? And that'd be a tough one to look at without using a graphing calculator. So rather than to have you do this as an exercise, I think it's more important to understand how to do this from the sense of, this is an equation that models this versus trying to figure out what exactly it is, because they go through in detail with a calculator on their book solution how their graphing calculator gets the answer. So to expect that is not something I would have you do, just because of the fact that not everybody in the class has one. So this is how you would get an equation to model this area of this one. And to find it, you would need a calculator to find the minimal area.